Check, check. Hi, everybody. Hopefully this is working. Just check here. Okay. All right. So this morning we're going to talk a little bit about chemical structures and how to draw them in some different ways, starting with some things that you've probably seen before, or you have seen if you did the worksheets from last module, and might be some new stuff as well. As we're going through this, just because this is the first time that we've done this like this, so I'm going to be doing all the notes here in our class notebook in the content library. So if you go into there, go to course materials, and then you'll see these here. We're going to be looking at this thing that was on Blackboard that's in here as well, and then drawing some stuff. So you can follow along there. You can also, if you have questions, you can leave them in the YouTube chat. You are going to need a Google account for that, but you can do that. And you can also send me messages on Discord or Teams. I think I should get them either way. So if you have a question, just send it over in the general part of the chat there, and or in the YouTube chat right here, and I'll answer it. It might be a little bit lagged depending on how real time the stream is, but as soon as I see your question, I'll go back and answer it. All right, so let's take a look at some chemical structures. So what you learned in the last part, or the last module, was something about how atoms are constructed. And so this next part, we're going to talk about how those atoms come together to form molecules. All right, so atoms coming together. And how they come together has to do with their electrons and the number of electrons. We'll get into those details in a little while. For now, we're going to focus on some very predictable bonding type situations so that we can make some sense of it, and it'll work for the structures that we care about, like our biodiesel molecules, things like that. So one thing to note is that certain elements are generally making certain numbers of bonds to other elements. So we can draw these lines, connecting two elements together like that. And we're going to see some common patterns that we'll explain probably in a couple of weeks when we get more into electronic structure. But we're going to see, for instance, that hydrogen generally only makes one bond. So when we see hydrogen, we're going to say generally that it makes one bond. So when it's in structures with other elements, we're just going to make sure there's one line coming from each hydrogen atom. Carbon, which is another one we're going to see a lot today, makes 4 bonds. And sorry for the messiness here. It's a little bit delayed from when I write it, so it gets a little tricky. But carbon generally makes 4 bonds, so we're going to see 4 lines coming off of carbon, and that can happen in a couple of different ways. So we can have, for example, we can have like this, where we drew here. But we can also have situations where we have multiple bonds between carbon and another atom. Move that over a little bit. And here. No, doesn't want me to move it over. Okay, well, that's fine. We'll go down here. So carbon can have these types of structures as well, where we would still consider those as being connected 4 times. So each carbon has 1, 2, 3, 4 lines coming off of it. It's just that 2 of those lines happen to be between the same 2 atoms. And carbon can make triple bonds as well. So you can have structures like this. Wow, it really doesn't like me moving this thing around, huh? Okay, well, we'll do what we can. Okay. And then the last one we're going to look at today is oxygen. Generally, oxygen is going to make two bonds. All right. So now that one is not quite as much of a rule as the other two. We will occasionally see structures where oxygen has one or three bonds, but at this point, if we just remember hydrogen makes one bond, carbon makes four, and oxygen makes two, then we can start putting together some chemical structures that make sense chemically. So we can, for example, take a molecular formula like C4H10, and we can think about what that might look like structurally. So in order to do that, we would imagine that we have our pieces, and we can actually try this in lab. You can take models and like try to put stuff together. But we imagine we have, four carbon atoms and 10 hydrogen atoms all kind of sitting there, and we're going to put them together in a particular way. So in this case, we could go, all right, well, what happens if we just connect all the carbon atoms in a line? That's a good place to start because we know from our previous rules that hydrogen only makes one bond. So we can't put any hydrogens in the middle because anything in the middle is going to have at least two bonds. So we know we can't put the hydrogens there. So maybe we just put all the carbons there first. And that way the hydrogens can be on the outside. Like that. All right. And then the last thing we have to do is check that everything fits. So we always want to check two things. One, that we've used all the appropriate atoms, so we actually have the right numbers of each atom. And then second, that we're fulfilling those rules that we saw earlier. So we want to make sure that everything that needs a certain number of bonds has that number of bonds. So hydrogens can only have one line, carbons are always going to have four. So let's look at the structure and see if we can analyze it. So we see 1, 2, 3, 4 carbons. So that works. We see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. That works as well. And then we fulfill our rules also. Each hydrogen has one bond, and each carbon has four connecting to it. All right, so that's a good structure. So we would say this is a chemically reasonable structure. It fits the rules of chemistry that we would expect. But also, we should note that that is not the only possible structure with a formula C4H10. There is another one that looks like this. We still have to have those carbons in the middle, so we put those first. But we can connect them in a slightly different way and make a different structure. All right. And so now this one still fits all the rules. We've got four carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. But they're connected in a totally different way. Instead of being connected four carbons in a row, two carbons that have two others connected, and then two on the ends, we now have one in the middle that has just one hydrogen connected to it, and then three carbons with three hydrogens around the outside. So those are two different structures, and there's a word for that. These are called isomers. Isomers are different structures with the same same molecular formula. So we'll say different connections or connectivity, same formula, so the same numbers of atoms. All right, so some of you, those are the only two isomers of C4H10. And if you're looking closely, you might think that there are some other ones as well. So let's talk about other possible ways of drawing this that are not isomers. So for example, what if we went like this? What if we drew our three carbons in a row, and then we drew the fourth one down like this, and then put our hydrogens around the outside? So as it turns out, this is actually the same as the straight line one that we drew earlier. And the reason is that single bonds have free rotation in the molecule. So if we built a model of this, you could kind of twist it and spin it, and we'll maybe try this in class on Wednesday, where you can make these turns and spins. And so any kind of just bending or changing angles doesn't make a different structure. Another way of seeing that, that's going to kind of bring us into our next idea, is we can think about the ways that the carbons are connected to each other and the hydrogens that are connected to them. So we might describe this structure as a carbon with 3 hydrogens, then a carbon with 2 hydrogens, then a carbon with 2 hydrogens, then a carbon with 3 hydrogens. And if we go back up to our original one, or actually we can just redraw it here. We can see that that's the same situation. A carbon with 3 hydrogens, a carbon with 2, a carbon with 2, and a carbon with 3. So those end up being the same structure. Whereas if we look at this isomer up here, we can't describe this way. We can't even say that the carbons are connected in a line, because they aren't. We've got a carbon with 3 hydrogens connected to a carbon with 1, and then that carbon is kind of branched off into 2 other carbons with 3 hydrogens attached. So those are a little bit different. All right. So these types of structures that we're drawing are called Lewis structures. You don't need the quotes, I guess. They are just called Lewis structures. That's what we call them, named after somebody named Lewis. And they always show all of the atoms. So all the atoms in the molecule are drawn as letters with lines connecting them. And those are called Lewis structures. But as you might have noticed, it takes a while. And as these things get bigger and bigger, it really starts to take a while. When we start looking at the biodiesel molecules, you'll see those have something like 60-ish carbon atoms. And if we were to draw each one out and each hydrogen out, it would take forever to draw those things. So we need a more efficient way of expressing structures where we don't lose information. We still want to know, how are these things connected and so forth, but we want to be able to express them in a more condensed fashion. And so we have another type of a structure called a condensed structure. And condensed structures, that word condensed, means that the hydrogens are sort of pushed on or condensed or made smaller onto the carbons. So rather than drawing the molecule like this, we'll use this first one that we started with. We can instead draw that as CH3, CH2, CH2, CH3. All right, so that's the same structure as this one, but instead of drawing a line for every single hydrogen, we condense the hydrogens down on each carbon and write them after the carbon with their number of how many there are. So this is a carbon with 3 hydrogens coming off of it. This is a carbon with 2. This is a carbon with 2. And this is a carbon with 3. So in that way, we can express the structure in a more condensed fashion. Now, in fact, we can actually condense this further. So another problem that comes up sometimes is drawing structures or typing structures into a program like Word or whatever, where you have to, drawing symbols and things, lines, laying things out in weird directions just doesn't work that well. So instead, we can condense this even further and just put the atoms right next to each other like this. So you might see condensed structures written like this as well. So that way, that's very easy to type. All we need is a way of doing the subscript for the numbers. But when we draw a structure like this, or even like this first one, we need to know a little bit about chemistry to be able to understand this, because we need to know those original rules. Like, we need to know that this does not mean 3 hydrogens in between. And how would we know that? Well, if we try to draw this out, if we thought that this meant something like this, the CH3 meant 3 hydrogens in a row between the carbons, the only way we would know that that's wrong is by understanding those rules that we talked about earlier, that carbon needs 4 bonds and hydrogen needs 1 bond. So this doesn't follow those rules at all. The hydrogens have 2 bonds, the carbons have 1, and so that's not going to work at all. So we can know now that that's not correct. And so by knowing a little bit of chemical information, we can use a much easier way of expressing these structures. All right. But what if we go back to this other structure that we were using? See if I can copy it over here. No, maybe we're not going to do that. Did I just like paste it a bazillion times somewhere? Okay, maybe that doesn't work here. So let's just redraw it. Sorry, still getting used to this system. So this is the one that was like this. All right, so how could we express that in a condensed structure? Well, the easiest way is to do it the first way. So keep the lines between the carbons there and just condense the hydrogens. And that's totally a fine way of doing it. So we'd have a CH3 over on the left, and then a C with just 1 H in the middle, and then a CH3 over on the right, and then a CH3 up here. So that's one way we could do that. And that's a fine condensed structure. But if you really wanted to be able to express the structure in just one line, there's a couple ways we could do that. We could do it with parentheses. So we can use parentheses to indicate more than one group connected to something. In this case, we've got 3 CH3s all connected to that central CH. So we could draw this as CH3 in parentheses 3. So there's 3 of them all connected to that central CH. Obviously, that's less obvious compared to this first one. This one really shows you the structure really nicely. But if you were really restricted to one line, you could express the structure this way and still have the same amount of information. Again, because of our rules, we know that the CH3 that doesn't mean that they're all in a line, because CH3 is carbon with 3 hydrogens, which means it only has 1 spot left for another bond, because we need 4 overall. So it can't just be in a row. It has to be branching off somehow so that it's right on the end. And so with a little bit of playing around, you could get to this structure from here. And so the first part of the work for this module, if we look over at the chapter here, the first part is working with that. So working with how do you deal with moving these Lewis structures and condensed structures around. So you'll see there's a whole list of condensed structures, and then it asks you to draw a Lewis structure for each one. So let's see if we can pull one of these out and give it a try. Oh, it's going to make me take the whole thing. Okay. Let me try a different way here. I wonder if because I'm in the browser, I can't paste here. Maybe? It's thinking about it. Okay. Well, that takes a little while, but I guess it works. Let's move it over here. All right. So that's in the this is one of the ones from the book. So it's CH2 and then this double bond over to CH, CH2O, CH2, CH, and then parentheses CH3 2. Okay. So how do we deal with something like this, putting it into a Lewis structure? Well, the first thing I would do is expand it from this super condensed state. So I would like bring it out a little bit with the lines. So let's do that first. And really, we can just kind of follow the structure along unless we get into trouble somewhere. We can go CH2, and then we've got a double line to the CH, and then a CH2, and then O, CH2, CH. And so here's where I have to think a little bit. At the end, I've got CH3 2 in parentheses. So does that mean I'm going to put them like next to each other like this, or branch them off? And again, the answer comes from the number of bonds. We know carbon has to have 4 bonds and hydrogen just 1. So if we have CH here, then that's not enough bonds. That carbon only has 3 connections. 1, 2, and the hydrogen makes 3. So that can't be right. And then if we look over here, like this middle carbon, this carbon actually has 5 connections right now. It's got 1 here, 1 over here, and then 3 from the hydrogens. If we drew that out, right, that's a CH3, so that means 3 hydrogens. So that can't work because that carbon now has 5 bonds. So we know that that's not right. And it's totally okay to do some trial and error here, to write it down, try it out, see if it fits, and then when you realize it doesn't, you go back and try to fix it. So let's see what that would really look like. So really we should have 2 CH3s coming off of this middle CH. And that way, sorry, weird H here. That way, the C here is going to have 1, 2, 3, 4 bonds, and the C here 1, 2, 3, 4, and the C here 1, 2, 3, 4, and we're all good. So that kind of expands it out a little bit. And now when we go to the Lewis structure, we just have to expand the hydrogens off the carbons, and then do our checking, of course. So we've got a C with 2 H's. At this point, don't worry too much about whether your H's are coming straight off or at angles. We just want to make sure we have the right connections. Whoops. So you can see it's not beautiful here. I'm kind of getting in my own way, which is why condensed structures can be really helpful. But that would be a Lewis structure for this condensed structure. All right, so first step of the work, look at the condensed structures and try to bring them out into bigger, fully drawn structures. Okay. So then the next step is something that we call line structures. And line structures are even further abbreviated, but they're very nice and easy to draw and still give you all the structural information. And so moving forward from now, whenever we talk about these types of structures, we're generally going to express them as line structures or maybe sometimes condensed structures. When you look at structures of molecules, whether it's on in a textbook or on information about medications or things like that, they're almost always drawn as line structures. And so this is a really crucial part of our communication for the semester because this is how we're going to draw most of our molecules. All right, let's go back to that first one that we've been dealing with. I'll draw the condensed structure here. All right, so there's that molecule is called butane, by the way. So there's our condensed structure of butane. And then I'm going to draw this line structure, and then we'll talk about what it means. So here's what the line structure would look like. Okay, that's it. That's the whole thing. That's the whole structure. All right, so what's going on here? Well, you might be able to figure it out that we have 4 carbons. We're going to write little numbers here to keep track of them. And those carbons are represented by the ends and the changing of direction or intersections of the lines in this structure. Okay, so those 4 carbons are represented in the line structure by ends of lines and places where lines meet. You'll also notice that the carbon atoms aren't shown at all, so we just have those little points to call carbon atoms. And then the hydrogen atoms aren't shown at all either. That's probably the biggest abbreviation here. How do you know that that structure is CH3, CH2, CH3 if the hydrogen atoms aren't drawn? And so the key here is that we know carbon has to have 4 bonds. So we can figure out how many hydrogens go in these spots by counting up the number of extra bonds that each carbon atom has to have. So let's take a look at this one on the left, number 1. If we think about just that little atom right there, and we think how many bonds are shown, well, we can see that 1 bond is shown here, right? One there. So this carbon has 1 connection to it. And that must mean that there are 3 other connections somewhere because we know it has to have 4. And so those 3 other connections are the 3 hydrogens. If we move over then to number 2, same thing. We look at what's shown there, which is carbon with 2 lines. And then we know there must be 2 other connections there. And those represent the hydrogens. So a couple of rules about line structures that we can write here. Sorry, dropped my pen. And actually, you know what? I can type in here. So I'll just type. All right. Line structure rules. This might be a little hard to see on the video, but you can see it in Teams. So, line structure rules. 1, carbons are represented by ends of lines and intersections of lines. Okay, 2, hydrogens attached to carbons are not shown. And one important part here is this attached to carbons part, because as we'll see in a minute, if we have other atoms like oxygen, those hydrogens are still shown. We don't get rid of those, and that's because those other atoms aren't quite as predictable in their bonding. So we can't say exactly how many hydrogens are there unless they're shown more explicitly. All right, and then one thing I didn't really talk about was the angle. And so in this case, we can't use straight 90-degree angles because if you just draw a line, you don't know how many intersections that is. So we use the back and forth to show the intersections. And then conveniently, it's also how these structures look in real life, in terms of that's actually how carbon atoms bond is at those particular angles or at about those angles. So when we build models in class, you'll see a little bit about how that works. Okay, so the hydrogen atoms are not shown if they're attached to carbons, and and that's pretty much it. I'll also say try to make the largest angles possible. And what I mean by that is, let's take a look at our other structure, this one, and think about how we would draw a line structure for that. So when we're drawing a line structure from a condensed structure, what I like to do is try to find the longest chain in the structure. So the longest continuous carbon chain, the way that you can kind of draw with your finger and hit every single carbon atom along the way. And in this case, that's 3. 1, 2, 3, or 1, 2, 3, or 1, 2, 3. Whichever carbon you start at, you can only get to 3 carbons total before you have to pick up your finger and touch somewhere else. So that means we can start with a 3 carbon zigzag, which is going to look like this: 1, 2, 3. And it doesn't really matter how I draw it. We could draw it this way. We could draw it. Let's try a different one actually. We could go like this, right? 1, 2, 3. And so let's say we do this one, and then we need to put in that 4th carbon. So it's connected to the middle one, and we have basically 2 choices of how to put it in there. We can put it here, or we can put it here. And so this last rule, try to make the largest angles possible, tells us that this is actually the better structure. So even though in our condensed structure, the CH3 goes upwards, it doesn't actually matter because these things are, in space. They can spin around, flip around, move around, whatever. So we could imagine that as being upside down, and that way we can draw the carbon coming off this way, because this other one gives us a smaller angle here, kind of a cramped angle. So we want to kind of spread everything out as much as possible. So that's what our line structure would look like for this molecule here. All right, let's jump back to the book and see if we can try something. So once you feel good with the condensed structures, the book also goes through all of this material about line structures. So you can see their example and then their example there, and kind of how to read the structures, how to decode it. So definitely go through this stuff if what I'm saying isn't making a whole lot of sense, or if it does make sense, but you're still not, you're still having trouble with the problems when you're checking yourself. But once you feel good about it, down here, there's a bunch of tests. So drawing some bond structures for each of the following compounds. They start with some Lewis structure style ones, and then get into more condensed structures. So when you do the condensed structure ones, you're going to want to expand those into a Lewis structure first before trying to put them in the line structure. But let's just take one of these as an example and draw some line structures for them. All right, let's see if I can get this back in there. So I'm going to pull in those first 3, and we'll take a look at how we would draw line structures of them. Once we actually get it here. Oh no, that's the same one from before. Okay, well, never mind then. Let's try one more time because I really don't want to try to have to draw this thing. If you're watching later, you could just fast forward till when we figure it out. Let's see if it works this time. Okay, yeah, we got him. All right, great. Okay, let's take a look at this. We'll do the first one and the third one. Actually, I think we'll do all three as an example. All right, the first one, we've got a lot of stuff going on here. So again, I'm going to use that same strategy of finding the longest chain of carbons, making that my original zigzag, and then branching everything else off of that. So in this case, I can see 1, 2, 3, 4, 5 across the middle. I didn't have to go across the middle. I could have made a turn up to here or up to here. And you should be careful with this. Sometimes the longest chain is actually one that goes a weird direction or zigzags around. It doesn't have to just be straight across the middle. But this will give us a good route to start. So we need 5 carbons to start with. 1, 2, 3, 4, 5. And then it's also a good idea to number them off just to keep track of things. You know, technically the numbers aren't a part of the structure, but sometimes it's easy to actually accidentally get an extra zig or zag in there and then have the wrong number of carbons. So let's, now that we've got those, we can deal with this branching thing. So we're going to look at where the other carbons are and add them to our structure. In this case, we've got one more coming off of carbon number 2. So we'll put that there. And then we have 2 coming off of number 4. Now, we could put them like this, and it's not technically wrong to do that. But because of that issue of trying to spread things out and have the biggest possible angles, it's usually more correct to put them both on the same side like that. And so that's our finished line structure. That's it. And so you can see how nice and easy it is to make relatively large, draw relatively large structures using this technique. Okay, moving to the second one. Nothing really fancy here. Here's an example of where it does kind of turn the corner. So rather than just look at the middle 3 and say, well, we're going to go 1, 2, 3, we can start up here somewhere or down here, and we can go 1, 2, 3, 4. And so that will start us off with a 4-member zigzag, 1, 2, 3, 4. And then we just have a couple other things to add. We've got number 2. There's a carbon there, so we're going to put an extra carbon off of number 2. And then we've got this double bond to oxygen coming off of number 3. So we're going to leave that there and really not change anything. You'll notice in this particular book, there are these little dots on the oxygen. That has to do with counting electrons, and it's really important for organic chemistry to keep track of all those electrons. But for our purposes, it's not important at this point. So we're going to just leave those off. When you see those in these practice problems, you can just ignore them. So this will be our structure. Again, I drew the carbon up and the oxygen down because I wanted to spread things out more and not have it cramped in between those other 2 lines. All right, so just to check everything here, 1, 2, 3, 4. So we've got this thing coming off of number 2. Yep. And then we've got the oxygen double bond coming off of number 3. So it looks good. Okay, for the last one, I'm still going to start from the thinking about the carbon chain. So 1, 2, 3, even though it's oriented in an up-down direction instead of a horizontal direction. And then it's up to you how you want to orient this when you draw it. So you can keep that up-down direction and draw your zigzag like this, or you can flip it and go like that. You know, either way works fine. We'll just keep it like this because that's how it's drawn. For this one, just to give ourselves a little change. So there's our 3 carbons. And all we need to do now is add in those OHs. Now, a key to remember is we have to, in our structures, keep the hydrogen that's on the oxygen. We can only ignore the ones on the carbons because we know how many are supposed to be there. We have to keep the ones on the oxygen. And then another thing to keep in mind here is we're not going to put the OH right here because that's a carbon atom. So if we want to express that there's also an oxygen connected to that carbon atom, we have to draw another line coming off of it, and that's where we're going to put the O and the H. All right, so we can't put it directly there, or else that's not a carbon anymore. That's just the where the OH is. When we draw this line out, because we see the OH here, we know that this end is not a carbon, and this is just where the OH goes. All right, we can do the same thing with number 3, and then for number 2, we're going to flip it back on the other side for room. And then when we do something like that on the other side, because the carbon and the oxygen are the ones connected to each other, we often flip that. So instead of saying OH, we would say HO to show that the O is still connected to the C. All right, there are some other ways we could stretch out and draw this structure too. Let's look at how we would do it horizontally. So let's say we went like this with our carbons. 1, 2, 3. So then when we're adding in the OHs, we could maintain that same shape as we did up here, or we could keep the zigzag and do that over here. So we can put our first HO connected to the C, and then our second one right there, and then our third one over here. So that would be another way to draw that structure. Again, these are the same. These are the same. They only differ by rotation. If you imagine here, if we like flip this over and then flip this one over, twisting around these two bonds, we would have that same structure once we rotate it. So some difficult three-dimensional thinking about things in your head here sometimes, but this is how you draw those line structures. All right, so this week, you should definitely make sure that you go through this reading, and more importantly, that you try out all of these problems. So, I would just work through them one by one, drawing the structure, and then checking them against structures that your classmates have drawn. This would be a great way to collaborate, work together, share your structures with each other. Or you could, if you draw them right in OneNote, you can send me a quick note and say, hey, can you take a look at my notebook? I'm drawing these structures and I want to know if I'm on the right track. And I can pull up your OneNote notebook and see how everything looks. So that would be a great way to collaborate on those. You could also just try them on paper, bring them into me on Wednesday. We can check them out. And then when we start this session on next Thursday, before going into the new material on polarity, I'm going to go through some of these and show you some examples as well. There's also a couple examples here that are not quite for us. So let me just mark that here. So like this bottom one, we haven't talked about that stuff yet. We might get into that next week. And then a really nice, interesting activity here is that we didn't do together is this number 2.5. In this case, you're being shown a bunch of line structures, and you have to figure out how many of each atom is in there. So you have to accurately count the carbon atoms and the hydrogen atoms to make sure you've accounted for everything. And there's some kind of weird, tricky connected ones too. So give those a try and let me know how it's going. And maybe on Wednesday there will be some time to check answers and to think about how you're going to move forward with this objective. But we really want to make sure that you can draw structures like this and interpret them because we're going to be using them for all the stuff later in the semester, including even just now describing our biodiesel reactions. So next week on Thursday, we're going to describe biodiesel reactions together like this, or if we have time, we could do it in class on Wednesday. And then we'll look at polarity and intermolecular forces. All right, well, hopefully this worked out okay. And let me know if there's any issues with the video or if you're having trouble accessing things. And I will see you on Wednesday. Bye, everybody.